Good morning. I'm Spot On Weather meteorologist Matthew Euler, and we're going to take a look. My special video has finally arrived, the 2019-20 winter forecast, and we're going to take a look at quite a few factors actually in what I'm weighing towards in my forecast for this upcoming winter. Now, this picture here shows a past snowstorm across the Hampton Roads, Virginia area. This forecast is primarily focused for the Southeast Virginia Hampton Roads area. But I will be discussing quite a bit of interesting tidbits here about the upcoming winter in this video. All right, so first I want to start off with a talk about my winter outlook considerations. All right, these are the main considerations that we look into each winter in developing the winter forecast. All right, I want to really emphasize this year I'm focused on the Pacific more than ever because last year, and I'll show you a rehash of last winter here in a minute. Last year it just did not, that Pacific played such a huge role. You know, we were supposed to have a weak El Nino and it didn't even materialize until late winter, which threw a lot of things out of what you'd expect, out of the norm. This winter, what we're looking at is El Nino Southern Oscillation phases. It's abbreviated ENSO, ENSO. The North Atlantic Oscillation, abbreviated NAO. The Arctic Oscillation, abbreviated AO. And their phases for the NAO and AO are huge because we're on the East Coast, and that has a huge implication on what happens across the North Atlantic and the overall long wave pattern. The Pacific North American pattern, that PNA, and then the Madden-Julian Oscillation, the MJO phases. The Madden-Julian Oscillation, Pacific North American pattern, those really came into significant play last winter, the winter of 2018-19. Low solar activity. Now this is a newer one this year that I'm really taking into account for the upcoming winter forecast. And typically, done by past research, lower solar activity is associated with high latitude blocking and a weaker polar vortex. So I find it really fascinating. You know, last winter we were in a low solar activity cycle, and we did see that polar vortex weaken, become unstable, and a lot of cold Arctic air had plunged into the lower 48. I'm really interested to see how this plays out, but I do have some emphasis in the low solar activity area this winter. And then hurricane accumulated cyclone energy. Accumulated cyclone energy being abbreviated ACE or ACE. Now, we've done a little research here at Spot On Weather, and we've come to realize that potential energy, ACE basically is that, and I'm going to go further into it I'm going to break each of these down, but with ACE, that's potential energy for East Coast winter storms. And that's gonna have a huge implication as far as whether we have a southeast ridge or a mean trough over the East Coast during the upcoming winter. Now, we also look at the sea surface temperature anomalies over the eastern North Pacific Ocean, as well as polar vortex stratospheric warming events, which we had a significant stratospheric warming last year, and I'll get into that here in a minute. But I just wanted to really, my main focus, I'm going to talk about weighted factors towards the end before I show you my winter forecast for this upcoming winter, the 2019-20 winter. But if you look at some of the main Pacific influences, everything moves from west to east. The winds generally blow from west to east across the mid-latitudes. So if we look at Pacific influences here, we're looking at ENSO, the El Nino Southern Oscillation. The PNA is set up by the sea surface temperature anomalies across the eastern North Pacific. The Madden-Julian Oscillation phases, these can be significant and fairly amplified and have huge impacts on the forecast. Again, that's a Pacific factor as well. So we do have a lot of Pacific influence here in this winter's outlook, in my winter outlook this year. All right, first let's start off and take a look at a summary of last winter. Now this was the winter of 2018-2019, okay? It got off to an interesting start across Southeast Virginia. I posted a video on the Spot On Weather YouTube channel, and I took a video of some rain mixing with snow on a early December day, back on December 5th of 2018. It was actually a mix of rain and snow across Hampton Road cities, And you look at that, and temperatures were 41 degrees Fahrenheit. And you look at that and you say to yourself, "Ooh boy, this might be a bad winter because we're already getting snowflakes mixed in with rain." It turned out to be the exact opposite winter last year than what I was expecting, especially considering I was going with a weak El Nino forecast, and I was relying heavily upon that as my primary weighted factor in last year's winter outlook. Now, last winter, we had a lower than average number of nor'easters. For long stretches into January and February, everybody was scratching their head, including myself. And there's a lot of people out there going, where are these East Coast winter storms? Where are the nor'easters at? Oh my goodness. We had a complete void of nor'easter type storms. Many forecast agencies last year, they also went with a weak El Nino forecast for the winter. And, typically you get above normal precipitation into the mid-Atlantic with a weak El Nino. You typically get cooler than normal temperatures because you have a lot more cloud coverage. And so it definitely did not pan out. What happened last winter, and by the way, these charts are courtesy of the Atmospheric Environmental Research. Dr. Judah Cohen posted these after the winter concluded. So if you look at the image on the right, and I want you to focus really on that one, you see the reddish colors. The red colors indicate warmer than normal temperatures from December through February. December 2018 to February 2019, those are above normal temperatures. And you can see almost as if that's the shape of a southeastern ridge. While meanwhile, back towards the northern plains, the Dakotas into Montana, you had extremely cold temperatures. So we had a southeastern ridge that developed above normal temperatures are in red on the image on the right, the graphic on the right. From the southeast to the Ohio Valley and mid-Atlantic, it was above normal winter in temperature as far as temperatures go. The coldest temperatures, they stayed primarily over the northern plains during the heart of winter. Now we have the major polar vortex that came in, I believe it was later January and early February. Okay, that did drop temperatures temporarily to very bone-chilling levels. Wind chills were very, very low across the upper plains and the Midwest during late January and early February. But then the coldest air seemed to shift back towards the northern plains, and that's pretty much where it remained from February, pretty much the whole month of February. So we didn't have hardly any chance with that ridge in place, the southeastern ridge. We didn't have hardly any chance for any nor'easters or East Coast winter storms to develop, really. And last year was a winter season of near misses. We did have a couple intense lows try to develop, but they remained well offshore. And also I want to point out on the image, the graphic on the right, you see the reddish colors and then you see the blue. Where those meet, that typically forms a frontal, more of a stationary frontal boundary, what's known as a baroclinic zone. And those baroclinic zones are the major battleground spots for storms to form along. And so there was a way above normal precipitation back in the Midwest last year, especially up into the upper Midwest, such as Minnesota. Minneapolis had a very big winter in snow. So the winners of, if you like snow, the winners of the snow contest last winter were pretty much from the Midwest up to the upper plains, northern plains states. They got hit hard as we had low pressure after low pressure, storm after storm form along this baroclinic zone where the red and the blue colors meet there, stretching from Oklahoma to Illinois. So right along that boundary, that great temperature contrast, that's the energy storms use to really develop and intensify. You have a big temperature difference over a short horizontal distance. You're going to get multiple storms to form, and it seemed like this pattern was just stuck. February was, normally that's one of the colder, or especially early February is one of the colder times for Southeast Virginia, and that's usually when you get more of the snow from the 1st of February to 15 February climatologically. But there was just a major absence of East Coast winter storms last year. So this is how it turned out. And again, it is nothing what the weak El Nino would indicate. And so later in the year, I think it was back towards late February and early March, that's when the weak El Nino finally kicked in across the equatorial waters of the Eastern Pacific. And by that point, we were already heading towards March, and temperatures eventually started warming. All right, so let's first talk about El Nino Southern Oscillation. I'm going to break down my factors now. We're going to start with the El Nino Southern Oscillation, the ENSO. All right, so The Pacific Ocean. This factors significantly into how the upper air jet stream pattern sets up. Where are the long wave troughs? Where are the ridges? How's that configuration setting up across the northern hemisphere? And we have to look upstream, living in the lower 48 in the United States. We have to look upstream, and upstream for us is back towards the west. We have to definitely take into account the impacts of the Pacific Ocean on the winter season. All right, so the eastern Pacific Ocean, the equatorial area, that's known as El Nino Region 3.4. Now, El Nino Region 3.4, if you look at the bottom right of this slide, you'll see it graphically delineated. And then you also see, I put in the text there, the Nino 3.4 region is from latitude 5 degrees north to 5 degrees south and longitude 120 degrees west to 170 degrees west. Okay. Now, that area has shown signs of recent cooling. Okay, in the past few months, we've seen the sea surface temperatures get cooler in that area. That's important. We do have a la nada. Some people joke and say la nada, nothing. And so neutral conditions is forecast this upcoming winter. Now keep in mind, and I said this on last year's winter outlook video. I said this last year and I'll say it again because the emphasis is, I tell you, it's such a great emphasis here. No two El Nino southern oscillation winters are ever exactly alike. Ever. You know, just like a person has a slightly different personality, no two people are identically alike. It's the same in the atmosphere. Right? So last winter, we had a weak El Nino that was forecast, as I mentioned already. It was supposed to develop prior to the start of the winter months. That did not happen. That did not happen until late winter. And this resulted in conditions more typical of a La Nina winter, which is the complete opposite of what many forecast agencies were looking at last year. With a La Nina winter, we usually are milder and drier here across southeast Virginia. Okay, and again, the focus of the coldest temps last winter, the above normal snow occurred in the northern plains and Midwest, and there was milder and below normal snow across the east, even all the way up into New England. You know, Boston for the longest time, they were just wondering where winter was because they just weren't getting much in the way of snow at all. Okay, here's the graphics that back up the El Nino phases. These are the typical winter weather patterns associated with El Nino. These images are courtesy of NOAA. All right, so the image on the left shows a typical El Nino wintertime pattern. So you have an area of low pressure over the eastern Pacific, and you have a warmer air mass situated over the Gulf of Alaska down into British Columbia, all the way down into the Pacific Northwest and Northern Plains. All right. You have a subtropical jet stream that moves across the bottom of the screen there on the left-hand graphic. That red arrow, that's a subtropical jet stream, and it's fairly active. So you get a more active southern storm track. You get wetter and cooler conditions across the southern area, southeast U.S., Gulf Coast states, into Florida. And what defines El Nino? Okay, the Climate Prediction Center, NOAA agency, they characterize El Nino by a positive oceanic Nino index, ONI, greater than or equal to 0.5. We've got to be 0.5 degrees Celsius for above normal. 0.5 degrees Celsius above normal for sea surface temperatures for 3 consecutive months in the Nino 3.4 region. That's why I showed you this Nino 3.4 region specifics, where it's located. Okay. On the other hand, you look at La Nina. La Nina graphic on the right, and now you can see the polar jet stream sets up a little bit further north. It goes into further north into Alaska. So instead of a warm air mass area, you have a cooler air mass area in the Gulf of Alaska, down to British Columbia, down across the Pacific Northwest. What's interesting is the La Nina graphic on the right, that's exactly what we had last year across the U.S. for a good chunk of the wintertime. So you get a less active subtropical jet stream when you have a La Nina conditions, and you get dry and warm air, generally in Florida, along the Gulf Coast, back into South Texas and New Mexico. And you do have a dip in the polar jet stream across the northern plains, so it tends to be colder than normal across the northern plains into the Midwest, and that's exactly what we got last winter. Okay, so how does NOAA define La Nina? La Nina is characterized by a negative oceanic Nino index less than or equal to, so it's 0.5 degrees Celsius or lower. 0.5 degrees Celsius departure, cooler than normal sea surface temperatures for 3 consecutive months in that Nino 3.4 region. So there's a difference here between El Nino and La Nina, and this has been studied over time. We've had this El Nino southern oscillation cycle, every 3 to 7 years for quite some time back in history. The Climate Prediction Centers looked at this extensively, and this is typically the weather patterns you have with El Nino and La Nina. What about this year? All right, and I'm going to show you the models here in a minute, what they're forecasting from the Climate Prediction Center, but this is typical conditions associated with an ENSO neutral winter. Okay, so you do have wetter conditions across the southeast. See the green area there up into the mid-Atlantic. You have colder than normal conditions. You have a trough, an average mean trough that's situated from the northwest portions of Canada stretching down into the Midwest and basically runs right over the top of Virginia out to the Atlantic. So tropical jet stream is somewhat active. It's not fully active like it is with an El Nino winter, but it is somewhat active. You got warmer and wetter conditions down south along the Gulf Coast and Florida. And you do have a fairly active Pacific jet stream there. Right, so in ENSO neutral conditions, those are characterized by sea surface temperatures. The departures between, basically your sea surface temperature departures are between 0.5 and negative 0.5 degrees. So 0.5 degrees above normal to 0.5 degrees below normal Celsius in the Nino 3.4 region. Okay. This is the ENSO forecast probability, the models from the NOAA Climate Prediction Center. All right, the image on the left shows the probabilistic, the different colors represent different ENSO phases. So for example, the image on the left, if it's a blue bar, that is a La Nina forecast probability. If it's a gray bar, it's for neutral, ENSO neutral forecast probability. And then the red bar, the vertical bar, indicates El Nino forecast probability. Okay. Now the probability runs on the y-axis vertically, ranging from 0 to 100% on the left, and then the bottom, or the overall, the horizontal x-axis across the bottom, you got the months grouped up into 3 months at a time. Okay, so as we move into December, January, February on this graph, we can see that there is a greater than 50% probability. There's a greater than 50% probability we are going to see neutral El Nino ENSO neutral conditions for this upcoming winter. Okay, just slightly above 50, between 50 and 60% probability. Okay, now El Nino is second. It's just basically around 30% probability, and then La Nina is the lowest probability right now. It's December, January, February, DJF. The probability of a La Nina winter is about 18%. Okay. The image on the right shows the various forecast models, the climate models, as far as what they're predicting for the sea surface temperature anomaly in degrees Celsius for the Nino 3.4 region. And generally, what we're looking at, the blue line is the consolidated line, and that generally shows conditions ranging, if I go to December, January, February, we're looking at about 0.3 degrees Celsius above normal temperature departure for the water temperatures in the Nino 3.4 region. So in general, we're between that 0.5, the positive 0.5 and the negative 0.5 easily. Most of the models are in that window. Now, there are some models that go above 0.5 degrees Celsius departure from normal for indicating El Nino. There are a few that go above that, but for the most part, the consolidation, the majority of the models are indicating a ENSO neutral winter this year. Okay. And when I talk about Oceanic Nino Index, ONI, that's based on the sea surface temperature departures from average in the Nino 3.4 region. And what is it used for? It's principally used to measure, monitor, and assess and predict the ENSO. So this is very important here. We're looking at the models. So right now, the forecasted models via the Climate Prediction Center indicating a ENSO neutral winter. Moving on now to some of the oscillations, the teleconnections. These are huge in the winter. These are tricky to forecast. Overall, what you have is an image of the negative North Atlantic Oscillation on the left and a positive mode of the North Atlantic Oscillation on the right. And what we're doing is showing you the general setup of the jet stream in both cases. So you notice on the left with a negative North Atlantic Oscillation, we get this huge ridge into Greenland. We get this huge ridge and a blocking, high latitude blocking with a negative North Atlantic Oscillation. What that does is it causes the jet stream, basically you have a deeper trough along the east coast of the US, and it's typically colder and wetter than normal. And then you also get a dip in the jet stream into northern Europe where it's colder and drier than normal. This really impacts the tracks of nor'easters and east coast winter storms because with blocking off over Greenland over the North Atlantic, these storms cannot readily escape out to sea. So a lot of the near miss cases of the nor'easters each winter with a high latitude blocking in place, with the Greenland block in place, with a negative North Atlantic Oscillation, the storms tend to ride up along that jet stream and generally tend to move closer to the east coast of the United States. So this results in more intense nor'easters, longer lasting nor'easters especially, so it's a greater duration. The image on the right shows a positive mode of the North Atlantic Oscillation, and notice a warmer and drier eastern U.S. in this case, and the jet stream is less meridional, so it's more west to east or more zonal, almost like a horizontal line moving from west to east. And so in this case, you have warmer and drier conditions for the eastern U.S. What about the Arctic oscillation phases in weather? Example, a negative phase on the left shows a general high pressure at the higher latitudes, and you get low pressure at lower latitudes, so high over low, and you get a dip in the jet stream transporting with a negative Arctic oscillation. You get much colder air to move in from the northern plains across the Midwest to the East Coast, and you got low pressure now over the North Atlantic Ocean. If you look at the positive phase, we're looking at more of a west to east jet stream represented by those black arrows. The jet stream basically moves from west to east. It's a very fast moving jet stream. Storms are less amplified. You might get weaker disturbances or weaker storm systems that pass through every 2 to 3 days in this case. But you're not tapping into the very cold air that's situated over the Arctic with a positive Arctic oscillation. This is the recent history this year of the North Atlantic Oscillation and the Arctic Oscillation. And it's been really, really an odd situation in that from late spring through a lot of the summer, the North Atlantic Oscillation is on the left there, and the Arctic Oscillation, AO. The NAO and AO have pretty much been negative with high latitude blocking up into Greenland over the North Atlantic. So things have been really unusual. We did have a hot stretch of weather across southeast Virginia back in late July where temperatures were exceeding 95 degrees, but it didn't last too long. And yes, it has been a typical muggy, very warm summer here, but it hasn't been a very record-breaking summer. On the other hand, Europe has suffered through at least 2 major heat waves where temperatures were reaching all-time levels since records began. So the whole global pattern, the configuration of the jet stream, we're talking about teleconnections, the NAO and AO, that's huge. But it's really interesting how it's been primarily negative, the NAO and AO, from late spring through most of the summer. Just recently into September, where we're at now, it's actually become more positive. Another teleconnection pattern I like to talk about is the Pacific North American pattern, the PNA pattern. And there's just a quick look at it, what happens if you have a positive Pacific North American pattern, okay? You generally have increased chances of below normal temperatures across the eastern U.S. Basically, you get a western upper level ridge across the western U.S. with a positive PNA, and you get an eastern trough. And so you get colder and usually stormier weather across the eastern U.S. with a positive PNA. With a negative PNA, it flip-flops. You get colder than normal temperatures across the western U.S. with a trough, and you get above normal temperatures across the eastern U.S. with a ridge. And when you have negative P&A conditions, now this happened last winter. Um, this happened after the polar vortex outbreak across the Midwest and eastern U.S. The pattern shifted to where we had a negative P&A, where we had a persistent trough, or the jet stream was taking a dip out over the western U.S. So there was colder and snowier than normal conditions across the western U.S., including places like Seattle last winter. They got a snowfall up to 7 inches at one point. They had a couple different storm systems, which broke some records out that way because you had a persistent negative Pacific North American P&A pattern, and you had a trough and very cold air that came filtering in to the Pacific Northwest. Montana had one of the coldest winters in recent memory last year. And we continually across the southeast and even up to the mid-Atlantic, we had above normal temperatures. We were in that southeast ridge poked itself up. So in January and February 2019, we had that strongly negative P&A pattern. It persisted through the heart of winter with the upper level trough in the western U.S. and the ridge. Occasionally, the jet stream would kind of flatten out to become more zonal west to east, but it really didn't matter because we just didn't really have the right dynamics in place to create the East Coast winter storms in this type of setup. Next, teleconnection we talk about when I talk about the winter weather outlook, I have to look at this, the Madden-Julian oscillation, MJO. Now, what is the MJO? You may have heard of it before. If you follow any any meteorologists, any weather organizations, you'll hear them mention MJO a lot in the wintertime. This is a major fluctuation or change in tropical weather across the equatorial Pacific on weekly to monthly timescales. Now, the MJO is going to vary depending on where air is rising and where air is sinking. Again, it occurs in the equatorial Pacific Ocean, and it changes over time. Areas that have rising air and convection or thunderstorm activity versus areas that have sinking air. There's little waves that pass through the equatorial areas, and this results in enhanced areas where air is rising occasionally and then where air is sinking. Now, MJO plays a significant role and sometimes is even more dominant as compared to the other teleconnections. Sometimes the Pacific can be so dominant with the MJO that it basically trumps the AO and the NAO across the Atlantic. Weather being that it moves from west to east on the jet stream winds in the mid latitudes, so obviously the Pacific Ocean has a huge bearing on our winters. Now, milder phases of MJO are 3 through 7. There's 8 total phases for the MJO. The milder phases are 3 through 7 for the months of December, January, and February, while the colder phases are 8 through 2. In recent winters, we have seen a tendency for longer-term warmer phases and less amplified colder phases. We just haven't been in the 8s, the 1, and the 2 phases very long the last couple winters. This is what the composites look like for the Madden-Julian oscillation phases, December through February. If you look on the left, I have temperature composite. If you look on the right, I have precipitation composites. Okay, so if I look at the temperature composites, the blue colors indicate colder than normal temperatures. The orange and the yellowish colors indicate above normal temperatures. Okay, so again, just kind of show you for December, January, and February, phases 8, phases 1, phases 2 are colder than normal. See the blue shading? Are colder than normal across the eastern United States. Phase 2 actually is pretty cold across most of the United States. Whereas phase 3, phase 4, phase 5, and phase 6, phase 5, 6, and 7, all those are milder than normal conditions across the eastern U.S. And you'll notice by the time you get into phase 5 and phase 6, the orange colors are much brighter, which indicates greater above normal temperatures, higher temperature departures from normal. And so those phases 5 and 6 really, if you like snow, you don't like to see those. All right. Now the precipitation composites is on the right, and the green shadings indicate above normal precipitation areas. So if you see a darker green shading, that means you have even a higher amount above normal precipitation. Okay. So green shadings is above normal, brown shadings is below normal. And so you'll just compare the notes there for the different phases and what kind of precipitation you get. The next factor that I'm looking at for the winter outlook is solar activity. All right. This is a graph that shows how low the solar activity is right now. I mean, the number of sunspots are just really, really low right now. Okay, so this just shows you from going back to 1978. This graphic, this chart from 1978 to present. Okay, this shows you how the solar activity has changed, and it's based on the daily sunspot number. If you look on the left-hand side of the chart here, this graphic, you'll see daily sunspot number. So we had a high bump up in sunspot numbers, high solar activity in the range between 1980 and 1982. We had another bump up around 1990 to 1992. We had another increase, another peak there just about 1999 to 2003, and another peak there around 2014, 2015. And then in between those peaks, we've had some major drop-offs in solar activity. 1985, 86, it dropped. By the way, that was a very cold winter. If you look at 1996, 1997, another significant drop-off in solar activity. And then even lower solar activity, 2008 to 2010, which again, we had some fairly cold, below normal temperatures for the winter. And each of these valleys, or these low points on the graph, they correlate pretty well with like below normal temperatures across the eastern U.S. in the wintertime. All right, so during minimum solar activity, we have lower sunspot numbers, and we typically, research has indicated high latitude blocking is more frequent across the North Atlantic. So that associates with a negative North Atlantic oscillation and a negative Arctic oscillation. Sunspot activity is forecast to remain very low over the next 2 years. If you look at the Space Prediction Center, you can Google that, Space Prediction Center, and you can play around with their products. It's a NOAA agency, and they actually have a forecast for sunspot numbers. I've been keeping tabs on that, and it's very, very low. We're talking about less than 10 sunspots. So that it's very low right now. High latitude blocking in Greenland alters the long wave jet stream pattern, with a mean trough developing over the eastern U.S. and a mean ridge over the western U.S. Next, we move on to accumulated cyclone energy, ACE. These are the figures through the image on the right, the graphic on the right. That shows you the ACE accumulation cyclone energy through 10 September. All right, so the North Atlantic is, as of 10 September, had an ACE of 58. The average for the date is 48. So we're running slightly above normal in the ACE for hurricane activity. Now, what does ACE take into account? ACE takes into account hurricane intensity as well as its duration. So longer lasting, powerful hurricanes, just like we saw with Dorian recently, Hurricane Dorian down around the Bahamas at a Category 5, that just sat there and was spinning in the vicinity of the northern Bahamas Islands. Those really can raise the ACE up rather quickly. So thanks to Dorian, we have a higher than normal ACE right now across the North Atlantic. The Northern Hemisphere as a whole, though, we're below normal, 265.4. Normal for today's date is 291.1. If you look at the image on the left, the graphic on the left, it goes back to 1991. From 1991 to 2018, and shows ACE values. Shows hurricane seasons, accumulated cyclone energy. You'll see 1991 and 1994 was below normal for ACE. 95 to 96 was hyperactive. 97 went back to below normal, and so on. You can see the different ACE values. 2009 was below normal. All right, 2013 below normal, 2015 below normal. All right, and 2018 last year we were above normal again in the ACE value. East Coast winter storm activity. Let's take a look at that and how that and ACE have worked together here, okay? I got this data courtesy of Cornell University, and it's also NOAA data. But number of East Coast winter storms is indicated on the bars there on the left, the image on the left, showing you the numbers of each year, going back to 1949 to 2018. Shows the number of East Coast winter storms as well as strong East Coast winter storms, that number. Now, a strong East Coast winter storm, that is a storm with wind speeds exceeding 52 miles per hour. All right, so for example, last year in 2018, the total year now, not just the winter, not just last winter, but then we have to look at January and February of 2018, the previous winter, had 28 East Coast winter storms, 16 strong ones, okay? And you can just take a look at the different figures and see how the values and numbers have changed over the years. The graph on the right shows the actual graphical depiction. The image on the right shows that graphical depiction. And so you notice the blue color there. The blue color are the total number of East Coast winter storms. The red down at the bottom there, the red spikes, those are the strong East Coast winter storms. So you'll notice there's a lot of waxing and waning in the East Coast winter storm activity. There's a cycle there. There's peaks, there's valleys, and it goes up and down quite a bit. Okay. So this is what we have done research on spot on weather, and this is what we've come up with. All right. The lower the hurricane season accumulated cyclone energy, or ACE, the greater the likelihood of a higher number of East Coast winter storms, because this has to do with the conservation of energy concept. All right. The higher the hurricane season ACE, the greater the likelihood of a lower number of East Coast winter storms, because you have a void of potential energy. Simply put, atmosphere is always trying to achieve equilibrium or balance. If you have a lower ACE value, you got a quieter hurricane season in the North Atlantic. That means you have greater potential energy available in the western North Atlantic for East Coast winter storms to tap into. All right. Overall, you have an excessive potential energy. Eventually, that energy is going to be tapped into and it's going to be utilized via East Coast winter storms. However, if you have a very high number of hurricanes during hurricane season with a very high value ACE, above normal ACE, then you have a greater likelihood of a lower number of East Coast winter storms because you have a void. In that case, you have a void of available potential energy. The hurricanes have used up the potential energy, so you have a deficit. As of 10 September 2019, we're running slightly above normal again on the ACE, thanks to Hurricane Dorian. And Dorian's intensity, especially down as a Category 5 around the Bahamas, and its duration. This was a long-lasting storm that basically moved up along the east coast of Florida, continued moving up off the east coast of the U.S., off the Carolinas, and then pushed out to sea. So the ACE 40, that ACE value there in the parentheses, that's how much ACE, accumulated cyclone energy, occurred with Dorian, 47.8, and that storm lasted 15 days across the Atlantic basin. So yeah, that one really brought the values up. The ACE was very much below normal, well below normal before Dorian. Now, teleconnections and other forces are indicating a busy period of tropical cyclone activity in the North Atlantic Ocean basin for the remainder of this, well, at least over the next few weeks, as we get into late September, early October. Now, obviously, that could cause the ACE to rise to well above normal levels. The MJO, Madden-Julian oscillation, is forecast to be in phases 8 and 1, which favor greater tropical cyclone activity across the Atlantic basin. So this is the one really big wild card for me is ACE value, because the hurricane season does not end until the end of November. So we're really not going to get a good knowledge of the ACE value and how that could play into East Coast winter storms until later on. We're looking at about 45 to 60 days from now. Again, higher than normal ACE values during hurricane season, that equates to less potential energy available for East Coast winter storm development, and most likely a lower number of East Coast winter storms. That's only considering the ACE, not the other teleconnection factors. Southeast ridge is expected to be the main synoptic player. If that ACE ends up way above normal, let's say the rest of the hurricane season has strong hurricanes, long-lasting hurricanes, that means my accumulated cyclone energy, my ACE, is going to be much higher, and so that would tend to lead towards me favoring the southeast ridge developing again this winter, which means it would be a very mild winter, and it would also be very below normal as far as precipitation. So if the ACE ends up below normal, however, we could see a long wave trough develop over the eastern U.S. and remain in place. Next, I look at sea surface temperatures across the Pacific Ocean. This is huge, okay? These are the sea surface temperature anomalies. I got this this is CDAS. This is off of the Tropical Tidbits website. I circled the above normal sea surface temperatures there in the red outline, and then generally the type of jet stream pattern that results because of this in the wintertime. So that black line represents the typical jet stream when you have above normal sea surface temperatures across the northeastern Pacific, the Gulf of Alaska off the west coast of the U.S. you get a ridge, an upper level ridge develop over the west, and a trough to bring in much colder air across the Midwest and eastern U.S. down to the southeast. So again, that's the general development. That's the pattern you would get with those above normal sea surface temperatures in the wintertime across the eastern Pacific. Polar vortex and stratospheric warming events. All right, now we had a major stratospheric warming last winter. There's no doubt about it. And Dr. Judah Cohen, I'll share with you his information here in a minute. Dr. Cohen, he does an amazing job. He's done a lot of research. He does a lot of research on Arctic sea ice and developing a winter forecast. What does the Arctic sea ice look like? Is it above normal, below normal? But anyway, he does a lot of research on stratospheric warming events, polar vortex events. This is what happened last winter. Now, this image, these graphics show you 10 millibar, which is way, way high up in the atmosphere, 10 millibar temperature anomalies, as well as the 10 millibar temperature and geopotential heights on the left. So what you get in this case is, with the temperature anomalies, you get extremely warm air in the stratosphere above the Arctic areas of the northern hemisphere. You get this extreme warming. It's represented by that lighter color there, the reds, that lighter shading, it's almost like a lighter pink color that I got that big black arrow pointed towards. You get warming, excessive warming in the stratosphere, up to 10 millibars, and that will eventually cause the long wave jet stream pattern to change. The polar vortex then becomes unstable and weakens, and you get higher heights over the Arctic and lower heights across the mid-latitudes. And this allows for extremely cold air to dislodge itself into more southern latitudes, into the lower 48, into the U.S. And we talk about polar vortex events, we're talking about record-breaking cold. Arctic amplification is another topic that Dr. Judah Cohen discusses. He's done research on. What is that? Arctic amplification basically means a warmer Arctic leads to a meridional, more wavy jet stream pattern and more unstable polar vortex. That's going to lead to more extreme weather events, really. That's what it comes down to. When we talk about Arctic amplification, we're talking about the Arctic warming at twice the rate of the mid-latitudes, okay? And it's warming excessively. We're losing a lot of sea ice up in the higher latitudes now. This is the science behind the polar vortex. The image on the left shows a stable polar vortex, okay? The image on the right shows a more unstable polar vortex. And you'll notice how the jet stream changes. When you have a stable polar vortex, it remains over the North Pole. It spins. It's there every single year. The polar vortex is there every single year. Okay, but in the case of a stable polar vortex on the left, that's when it just continues to spin up over the North Pole, to the polar areas. And the jet stream is pretty much west to east. You get a strong west to east jet stream, but the coldest air remains north of that jet stream axis up over the higher latitudes up into the polar areas. If you get a wavy polar vortex or a weakened polar vortex, you get a lot more meridional or wavy type undulations in the polar front jet stream, and that's going to result in a lot of displacement of colder air towards the south. With a weaker polar vortex, if it's weak enough, it will come off the polar areas and come down towards Canada and eastern Canada, and it'll produce a lot of cold air. Will be pushed down into the lower 48. And again, just to rehash things, I'm kind of tying this in with the low solar activity. Research has shown that during low solar cycles, we see a greater likelihood of stratospheric warming and a weaker polar vortex. This was some of the sensible weather from last winter. The polar vortex, stratospheric warming, and this is the sensible weather you'd see at the surface where we live. Image on the left shows Chicago. Chicago was nothing but a big ice. That Lake Michigan was nothing but a big sheet of ice. See this guy walking there on the water? It just really frozen solid. You see a little bit of that steam fog coming up there in front of the buildings because the air's so cold. The air's so bitterly cold that you get the steam fog that comes up off the surface because the air is so cold aloft. And then the image on the right shows the minimum wind chill values That graphic's courtesy of Brett Schneider. The minimum wind chill values during the polar vortex event from January 26th to February 1st, 2019. The pink shadings, -50 to -60 degree wind chills. Okay, and that extended from eastern North Dakota, Minnesota, Wisconsin, eastern Iowa down to northern Illinois. All right, so the cold air really came down with the polar vortex being displaced late January and early February of 2019. Now, Dr. Judah Cohen he does a blog weekly, and there's the website for the blog if you want to jot it down. There's his blog right there, and I'll probably share this as we get closer to winter in social media and Facebook and Twitter. But he does an amazing job of just analyzing the trends in the polar vortex and possible stratospheric warming events. This is an example from AR, Atmospheric Environmental Research, and Dr. Judah Cohen again. This is the GFS ensemble showing the mean polar cap heights. Generally, I just want you to pay attention to the warmer looking colors on the graphic here, showing you when the upper stratosphere warms, generally stuff starts working its way towards the surface. We get colder, and you get what's known as troposphere, stratosphere, troposphere coupling, and you get colder temperatures. At the upper levels of the atmosphere heat up, you get the opposite in the lower levels. So this is a really good graphic that he uses often and talks about in his blogs. I just wanted to show you an example product. All right, so these are my amplifying thoughts. We take into account all these different teleconnections. I'll tell you what, this is a tricky forecast every winter because there's always competing factors every winter. And what do I mean by that? You may have favorable conditions like a negative NAO, but then you might have milder MJO phases, phase 5 and phase 6. And so, those two are offsetting each other. Or you might have positive NAO teleconnection phase, but then you have a colder MJO phase. Okay, it really comes down to, with competing factors, which factor is the most dominant, which one is the most influential. And that's the real trick in doing seasonal forecasts for the wintertime. Constructive versus destructive interference, I mentioned this plenty of times in past videos. And again, we talk about constructive interference, we talk about all the teleconnections aligning with each other. And maybe we have a negative NAO and we have a colder MJO phase. Maybe we have those line up and we get colder weather across the eastern U.S., a deeper long wave trough. Or we could have destructive interference where they offset each other. And it's kind of what I have in the parentheses I just mentioned. A negative NAO versus a milder MJO phase, or a positive NAO, which indicate warmer temps in the east, versus a colder MJO phase, which would indicate colder temperatures across the east. Timing. Timing is everything in an alignment of teleconnections. Okay, it's important for the alignment of all of them, the constructive interference, everything to be working towards the same results. And that doesn't happen a lot in the atmosphere. In the atmosphere, typically you have one factor working against another factor when we talk about teleconnections. If all factors line up at exactly the same time, that's when you get severe winter weather. And you also get the probability for more extreme weather. So which of the factors, here's my golden question of the video. Which of the factors that we discussed will predominantly influence the weather this upcoming winter? That to me is the most pressing question. And I look at this every winter when I create this video, and that is really it. I do not believe ENSO will be a major factor this winter because of the neutral conditions. I don't believe that one will be a heavy factor in what happens this year. I do believe that above normal sea surface temperatures across the eastern North Pacific could have a huge bearing on the long wave jet stream pattern. But do those above normal sea surface temperatures remain over the eastern North Pacific, or do those temperatures drop off closer to average like last winter? In 2014, we had extremely above normal sea surface temperatures in the eastern North Pacific, right off the west coast of the U.S. up to the Gulf of Alaska. That resulted in what was known as the ridiculously resilient ridge, triple R. And why? Because that ridge just stayed there day after day after day throughout that very extremely cold winter of 2014 into 2015 across the eastern U.S. Meanwhile, last winter, 2018-19, you had cooling temperatures, sea surface temperatures, and you end up getting a negative PNA over the Pacific Northwest into that area of the world. The other thing I look at, these are the questions I go through when developing this. I give it careful thought and consideration. Mean trough versus the southeast ridge. What are we going to see this winter? What is going to be the more predominant influence? And it's all going to depend on in my opinion, the Madden-Julian oscillation phase. When you get phases 5 and 6 of the Madden-Julian oscillation phase in the winter, that's when you typically have your southeast ridge in place. And that's where you get milder conditions up from the Gulf Coast to the Mid-Atlantic, and sometimes even further north than that. So are we going to have more of a long wave trough situated over the east or the southeast ridge? This has been a huge factor the past few winters. At some point each winter, the southeast ridge has extended northward to the mid-Atlantic, resulting in above normal temperatures and a lack of east coast winter storms. And again, it's most closely connected with the MJO phases. I'm heavily weighting this forecast, this outlook, on the Pacific Ocean current and forecasted conditions with Teleconnections. Here's my weighted factors in the forecast, and I put in red what would be the result for temperatures and precipitation for Southeast Virginia and the eastern U.S. as a whole. If we have a neutral ENSO, the average temperatures would be average. We'd have above average precip. With lower solar activity as a weighted factor in this forecast, that's going to lead to increased frequency of high latitude blocking, a negative NAO and AO. That will lead to below average temps and above average precip. The ACE, cumulative cyclone energy, how does that play into the East Coast winter storm frequency? If you have average ACE, below average ACE, and above average ACE, I delineated generally how that affects temperatures and precipitation. Stratospheric warming and a weak polar vortex, below average temperatures and below average precip. This is, as a result of all this research, all these considerations, this is my Southeast Virginia winter forecast. For the 2019-2020 winter forecast, I'm expecting below average temperatures and near average precipitation for Southeast Virginia, including near average snowfall. So we average in the Norfolk area about 7 inches of snow each winter. I'm expecting about that. December will feature mainly mild temperatures and dry conditions. Greatest probability for snow and coldest temperatures across Southeast Virginia, middle January to middle February is what I'm looking at. So I'm expecting a mild start to the winter. In December, it'll be fairly mild and dry. Then I think things will pick up between mid-January and mid-February. Expecting 1 to 2 moderate snow events, and I consider moderate 2 to 4 inch events. So I'm expecting 1 to 2 of those, or I could see one major snow event happening this winter. And that would be a 3 to 6 inch snow event across Southeast Virginia. That's if that southeast ridge is suppressed with a major nor'easter, where we get that explosive cyclogenesis over the Gulf of Mexico, and that explosive low rides up off the southeast coast. So that's what I'm looking at in red there. That's my official spot on weather. That's our forecast. Below average temperatures and near average precip, including near average snowfall, around 7 inches. Now, this is a preliminary winter forecast. Like I mentioned earlier, what's the ACE going to look like at the end of the hurricane season? All right. What are those sea surface temperatures going to look like a month from now, late October? So I will keep an eye on that, and I do plan to release a final winter forecast. This is more of a preliminary winter forecast, taking into account changes in those factors that we looked at. I do plan, if there's any significant changes from this outlook, to update that and post it. Final ACE seasonal value, again, yet to be determined and has a significant bearing on the forecast. Seasonal ACE values will not be known until the end of November, till the end of hurricane season. I am expecting this winter there will be periods of colder weather followed by milder weather. That happens every winter across mid-Atlantic, especially Southeast Virginia. You could have 57 degrees for a high one day, the next day is 40. And I do expect a wild swing in the temperatures. With the NAO and the AO being so negative for a majority of this past summer, I do expect an overall rebound to a positive North Atlantic oscillation and a positive Arctic oscillation. Nature has a way of working and balancing itself out. Low solar activity, that's real interesting. That will allow for periods of high latitude blocking and very cold temperatures. When we do have those colder than normal periods, I do expect the low solar activity to contribute to that with occasional high latitude blocking. Not a persistent high latitude blocking, more of an occasional one. I do expect a big battle between the southeast ridge and the eastern trough, cold versus warm battle zone. I think that baroclinic zone where that battle's happening, where you have the coldest and warmest temperatures next to each other, I think that's going to be a little bit further east-southeast this winter than last year. My wild cards are this. Now this could really throw a wrench in this. My wild cards are the frequency of East Coast winter storms. That's all going to be determined by the ACE values. We won't know the total final ACE values until the end of hurricane season, at the end of November. Again, if the ACE is below normal, we can expect more winter storms along the East Coast, possibly above average precipitation. That would impact my near average precipitation outlook at this time. That would actually raise up the values. But if the ACE is above normal, we expect less storms and possibly below average precip. That would also alter my near average precipitation forecast for the winter. The MJO phases, obviously if we get colder MJO phases 8, 1, and 2 developing for longer periods of time, we could see a potentially colder than normal winter. But on the other hand, it could flip and become, the last few winters we've seen more of the warmer MJO phases being amplified, being stronger, and lasting for longer periods of time. And one teleconnection can trump all of it, leading to a highly variable weather with wild swings in temperatures. Again, it goes back to our teleconnections working with each other or against each other. That's really the bottom line here. So that wraps things up. This is the official Spot on Weather Southeast Virginia winter forecast for this year, 2019-2020. We're in just about into the middle of September now. So I do expect some changes in some of this, especially the sea surface temperature departures in the Pacific. I do expect changes to that. I do expect changes to the ACE values, obviously dependent on how active hurricane season is. I do expect changes. We'll have to watch how the ENSO plays out, the El Nino Southern Oscillation. The low solar activity is locked in and it's going to be there. So that is going to favor those below average temps and above average precip for the eastern U.S. But overall, stratospheric warming and weak polar vortex, that one is going to have to be watched carefully as well, because you displace the polar vortex and it's usually about a 3-week delay between the displacement and weakening of the polar vortex, the warming in the stratosphere, and the actual sensible weather. So we have to watch that as well this winter. That could be a major wild card in the forecast. But as of right now, preliminary, below average temperatures, a little bit colder than normal. I'm expecting 1 to 3 degrees below normal Fahrenheit. When you look at the big picture, December, January, and February are the months I'm forecasting here. And the near average precipitation, December, January, and February. That wraps things up at Spot on Weather. I really hope you enjoyed listening to the winter outlook. Again, I will come back. I will keep an eye on things, and I will definitely highlight major changes between now and I might cut another video on the winter outlook closer to late October, early November, as we see how things change. So that wraps it up. Stay with us at Spot on Weather. We have you covered. We have a motto, and it's, if we're not spot on, we're not doing it right. We really are passionate about the weather. We enjoy the fact that you subscribe to the channel, and continue to follow us on Facebook and Twitter with the daily forecasts as well as the blogs. Check out the website, Spot on Weather on Weebly. Just Google Spot on Weather Weebly, and you'll see our link. And we have a lot of cool things on it. We have a photo gallery. If you click on the More tab, the upper right-hand portion of the website. We have a 7-day outlook for Southeast Virginia. We also have blogs, lots of weather photos. Oh, you got to take a look at it. Plus, you can take a look back at the past weather. I save the monthly weather summaries in there as well. Past significant weather events for Southeast Virginia are in there as well. So take it, got to check it out. I'm telling you, if you really enjoy the weather as much as we do, please check it out. All right, that wraps things up. Spot on Weather. I'll be back in probably 30 to 60 days with an update on the winter outlook. And as we get closer to the fall season, I'll start cutting a few more videos for the actual forecasting aspects and showing the models. All right, that wraps things up. Have a great day, everybody. Hope you stay safe and enjoy your time off whenever you have that. Take care, everybody.